Hello friends, good afternoon and welcome to EduSat live lectures. Dear friends, today in biotechnology we will be talking about proteins and their tertiary structures. To discuss this topic we have with us our subject expert Dr. Unnati Gulati. Dr. Gulati is academic coordinator in Consortium for Educational Communications, New Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you, Amrit. Dear students, we have been talking about protein structure and we did the hierarchy of the protein structure. We have done the primary structure, secondary structures, namely the alpha, beta and the terns. We saw what were the interactions that were responsible for the secondary structure. Then we continued into how the secondary structure underwent some forms of motifs and domains. Those were the super secondary structures that were formed and how they were incorporated into the tertiary structure. These motifs and domains we saw they were important for not only just structure, but they had some functional as well as evolutionary impact. So, you could study the protein on the basis of the type of domain present in it and correlate it to the function it may be having, or you can correlate it to the evolutionary history of the evolution of that protein, or you could find out how the protein, say we were talking about globins, and if we talk about the oxygen binding proteins, the hemoglobins and the like. So, we started off from the simplest leg hemoglobin which is found in the plants and how we can trace the ancestry of such a globin which binds to oxygen into the plants from higher animals, such as we have hemoglobin and myoglobin. So, besides that we will see now what are the interactions that will drive the protein from its primary structure to form a tertiary structure. We say that the hydrogen bonds are going to form and it is going to give it secondary structure. We also saw that the interactions were present which gave rise to further strengthening and compactness in the tertiary structure. So, we said that the globular proteins were polypeptides which folded up into compact and spherical shape. They had the shape and the structure which was important for their function, and they took part in all types of metabolic processes. And we took one example of myoglobin which has a prosthetic group for oxygen binding. So, some of the common features of these proteins we talked about was how some amino acids have tendency or propensity to be present either on the surface because they can form good hydrogen bonds. So, amino acids which are having a tendency to form good hydrogen bonds, here we have arginine, histidine, and they are largely located on the surface of the protein, while those which have long chain aliphatic groups, think about those amino acids valine, leucine, isoleucine, methionine, which will be present towards the core of the tertiary structure of the protein. And we saw that many of these charged group amino acids were located inside of the protein, but they were also responsible for some specific enzymatic catalytic activity, or where there has to be some binding to a ligand. The uncharged polar groups such as cysteine, threonine were also on the surface, but they were frequently found on the interior of the protein. So, if you look at the tyrosine and tryptophan, they are having some uncharged polar groups such as the OH group, also find in serine, threonine. So, these were located in the interior of the protein and they also formed hydrogen bonds. Hydrogen bonds are important. Why? Because hydrogen bonds can be formed inside the protein, the intramolecular intra-chain hydrogen bonding, and then there is another hydrogen bonding which occurs with the water which is present outside. So, this is how we saw the placement of amino acids, and we have been reiterating this fact when we first look at where these amino acids are found in the secondary structure, corroborated with the Ramachandran plot which told us that these amino acids have a particular tendency to lie in one of the quadrants of the Ramachandran plot. Then we also saw the Chow-Fasman rules, which related to these relating these amino acids to their propensities for secondary structure, and eventually we are also seeing that in tertiary structure they do follow the similar trends because of their chemical nature. So, we had done that tertiary structure can be globular and fibrous, and we will do details of globular and fibrous proteins. But let us first study the general aspects of tertiary structure. We have studied the electrostatic interactions in the last lecture, and we were talking about van der Waals and London dispersion forces. Van der Waals and London dispersion forces, as you can see from the example stated here, they all look like non-polar aliphatic groups except for phenylalanine. So, when we are talking about non-polar R groups, we almost always think about hydrophobic effect. So, how are we going to correlate the hydrophobic effect present as we directly see water heating effect, and how do we correlate it to van der Waals London dispersion forces? So, first thing is that these hydrophobic long chain R groups should have some degree of polarizability. So, when we say degree of polarizability, and we were talking about van der Waals dispersion forces, they get activated when two uncharged R groups come very close together, so much so that they cause disruption in the electron cloud of one of the groups, which in turn induces a disruption in the electron cloud of the neighboring molecule or R group, resulting in formation of dipole. One dipole is instantaneous, and it induces the formation of second dipole, and whenever there is a weak dipole, there are going to be attractive forces, and you have some electrostatic bond formed here. And we were talking about that these van der Waals forces were of very low energy, but being so numerous, if you see any primary structure of a protein, you will find that it has a balance of hydrophobic, it will have few hydrophobic and few charged amino acids present and few uncharged amino acids present here. As we go into this discussion of protein folding, we will understand why a protein is composed not entirely of one type of amino acids. So, the answer we will start taking from here. Van der Waals forces are very important. Non-polar uncharged groups which are amendable to, which can be polarized, will result in van der Waals forces. These groups, they also give the aspect of steric complementarity. We know what is steric hindrance and steric complementarity. You cannot make a molecule more compact than the allowed volume which is taken up by the atoms composing it. So, van der Waals forces will prevent a overlap or collapse of a molecule. Secondly, it also gives the possibility of polarization being induced into non-polar molecules, which can further result in binding. Although being very low in energy, several van der Waals forces or several such interactions will result in a higher enthalpy of electrostatics or higher enthalpy of binding. So, we were then talking about disulfide bonds. Disulfide bonds were formed from oxidation of the cysteine side group, and the SH was forming the disulfide bridge, and we saw that it was also in the intrachain or interchain. So, you will find it not only in the primary chain, but it will also result in quaternary structures such as in insulin. So, once we are through with those forces, we can talk about the hydrophobic forces. Very easily we know that there are some amino acids having R groups, which are glycine, alanine, valine, leucine. All of them have aliphatic R groups. Then you have phenylalanine and tryptophan, which have aromatic R groups. So, when we think of aromatic, we definitely think, okay, these are hydrophobic molecules which will not dissolve well in water or which are water hating. Similarly, is the case of long chain aliphatic groups. They also do not have tendency of forming hydrogen bonds. So, hydrophobic effect in itself is just not the amino acids which can which can be immiscible in water or which do not be immiscible in water. It is also responsible for what we talk about hydrogen bonding, and let us see how hydrogen bonding along with hydrophobic effect combine to give the aspect of the hydrophobic collapse of a polypeptide chain. So, first let us understand that the amino acids with the R groups, they are having non-polar R groups. So, non-polar R groups will have the tendency to like the similar kind of groups. So, like begets like, but these forces are very weak. Collectively they do stabilize the structure, and many a times we will say that how hydrophobic effect is important for the tertiary structure. In this case, these groups will repel all the water molecules away from them, and they will try to be present in the core of the protein. And let us again reiterate that it is not just the non-polar molecules that will come close together. Also remember, when such non-polar molecules come close together, they get to induce the van der Waals kind of interactions. So, we have to think about three things here: the tendency of an R group to be miscible with water or to be not miscible with water. Secondly, such R groups, they can form cores where only those aliphatic non-polar groups are going to be present. These cores are going to be always water hating, and once these R groups come very close together, they may result in the London dispersion forces, giving rise to ionic dipole-dipole bonds of van der Waals nature, not very strong bonds, but weak van der Waals interactions. Apart from that, when these molecules come close together, we will see when and why these molecules come close together and how hydrogen bonding affects this hydrophobic effect. So, here we will have to talk about not just coming close together of the non-polar, but how the water thermodynamics play a large role in this collapse. So, again we talk about the hydrogen bond. We look at it is a very flexible, transient or a flickering kind of bond when we think of water. So, water can undergo hydrogen bond and it is not very stable. So, if it is forming one hydrogen bond with the one molecule, in some time it will form hydrogen bond with the second, and it is because of the normal normal vibrational motion which is occurring in the molecule. So, it will be always be transient, and that is why we show it by dotted lines. So, this transient nature of hydrogen bonding is also very important. When I am saying transient, I am also talking about how it is going to be disordered, and when I am saying disordered, I mean entropy. What is the role of entropy in protein folding in the protein tertiary structure? We will see, and that entropy of the solvent is attributed to this transient flickering hydrogen bonding of water. We have seen that for forming a hydrogen bond, there is a necessity of an acceptor or a donor and a donor molecule. Acceptor here is a proton acceptor and a proton donor, and always you will find nitrogen and oxygen are going to be present. Even when you are forming hydrogen bonds, you need some electronegative atom to form hydrogen bond with water. Also, if you remember, we discussed this diagram in which we are showing the backbone hydrogen bonds that were formed, that you saw in the beta sheets as well as in the alpha sheets. So, there is going to be hydrogen bonding within the water, there is going to be hydrogen bonding with the backbone which gave you the secondary structure, and there is going to be hydrogen bonding within the chain, and this hydrogen bonding will also occur protein and the solvent. So, what is the balance of these forces and which ones are prevalent, we will see. So, let us say that all the electrostatic interactions, even water hydrogen bonding is a type of dipole-dipole interaction, a weak dipole-dipole interaction. So, all these electrostatic disulfide will contribute to the enthalpy of the protein folding. So, all these are the delta H bonding, and bonding to different extents, some are weak and some are very strong. So, we will see also what are the contributory effect of these electrostatic interactions. This hydrogen bonding, this is not just single term that we will be studying, and we will see where do we incorporate this term when we talk about overall stability of the protein when it is present in the solution. So, hydrophobicity and hydrogen bond formation. Simply put, if we have a protein which is unfolded and we have the hydrophobic groups exposed outwardly, it will result in its collapse such that there is bringing together the hydrophobic groups towards the core. So, all these yellow circles are hydrophobic groups which are present, which have been brought into the core, and when this is happening, the entropy of the solvent is going to increase, and as we said, all the bonds, they contribute to the enthalpy of the protein folding process. So, first let us understand what is hydrophobic effect in light of what it does to the water. Water is showing us the hydrogen bonding, while all the R groups, such as we see here, is a long chain aliphatic. So, all these are CH2, CH3, CH3. So, it is a long chain aliphatic. So, what happens to water around it, and how hydrogen bonding and hydrophobic effect are two sides of the same coin. So, whenever let us look at this diagram. So, in this diagram, whenever we have a droplet of oil present in water, why do we always find that the oil will not disperse well in the water? After some times, even if you shake it well, you try to mix it, it will come back as large globules of oil. So, what is happening there? Whenever we drop oil into water or mix oil into water, there is structuring of water around the oil. Oil and water are immiscible. Oil is an example of a hydrophobic, water hating molecule. So, here it is present as a water will arrange around the oil droplet and form a rigid cage. It is not extremely rigid as we would say, but in this case the hydrogen bond pattern is slightly different. The ideal condition for any hydrogen bonding, for it to be strongest, is that this angle should be around 135 to 180 degrees, but in this case it will form shorter hydrogen bonds within the neighboring molecules and form a rigid structure around this. Eventually, what will happen? These two droplets will coalesce and will result in only fewer molecules being placed in the rigid cage-like formation. So, what has changed here? In this one example, we see that there were several molecules, each of them surrounding surrounding the oil droplets, while here you have slightly less number of water molecules surrounding the oil droplet. This setup changes the entropy of the water. Water in this case, as you can see, is present and giving rise to all sorts of flickering hydrogen bonding. So, it may form a hydrogen bond here and later the hydrogen bonding pattern will change. When such water is introduced with a droplet of oil, all these flickering motions are restricted because it can no longer form hydrogen bonding with the hydrophobic oil droplet, and it has to form some rigid hydrogen bonding amongst itself. And we see here that how a cavity or a cage like hydrogen bonding with short distance and small angle is formed. You can see the small angle of hydrogen bond being formed here. So, when this angle is formed, it is caged, and I would say it is not just one layer, we show it as a one layer, but there are going to be subsequent layers beyond this also which will be in a rigid structure. When this rigid structure is formed around the non-polar tail of the hydrophobic molecule, this results in the orderedness of the water, and from the, just a minute. So, from this diagram we see when there is only one long chain hydrocarbon, there is structuring of water molecule all around it, and when we have two such groups coming together, we see that now lesser number of water molecules are packed around in a cage. This cage is somewhat similar to the ice like structure, and ice is not the entropically stable form of water. So, now we know that why hydrophobic molecules are going to come close together, so that they can result in increase of the entropy of water and eventually increase in the entropy of the system. And whenever there are more and more number of non-polar molecules coming together, more and more molecules of water which were structured earlier become free to be part of the bulk water, and hence it will result in the increase of entropy of the water. When it is increased further, there is hydrogen bonding, because more water molecules are free to form stronger hydrogen bonds, then it is going to contribute to the hydrogen bonding and enthalpy, and we will have a slightly stable conformation, or we can say we can have a slightly stable system. So, some of the examples of properties of hydrogen bonds we can see here is that you will find a stronger hydrogen bond if the angles are around 180 to 135, and you will have more weaker hydrogen bonds if you decrease the angle. Hydrogen bonds can be formed with many types of groups, mostly where you have oxygen, nitrogen groups, and water can form hydrogen bonds. So, these some of the examples. You will find hydrogen bonding present in peptide backbones and also in the structure of DNA. The DNA ladder is also having hydrogen bonds. So, hydrogen bonding is an important concept in structure, in water structure. Also, it is important, you can see there are so many amino acids which have are groups which can form hydrogen bonding with water. So, just summarize these, that valine, arginine, histidine, all of these alanine, they can form hydrogen water bonding with the water, and you have several orientations, and multiple hydrogen bond formation is also permissible. So, that is also contributing to the enthalpy. Also, in ligand binding, in this case, what is the role of hydrogen bonding? A hydrophobic substrate is coming close to the binding site, and once hydrogen bonding occurs, then only few water molecules are shown to be structured, while rest of are in the bulk, and otherwise what you will have, the substrate is also ordering the water and causing decrease in the entropy, and even the enzyme binding site is being hydrophobic is ordering and decreasing the entropy. So, binding is a favorable event which causes increase in the entropy of the of the bulk system. So, it is not just because of non-polar molecules that have interaction or that can form van der Waals forces, it is also because of water, and we have seen that several examples where hydrogen bonding is very important for protein folding, protein stability, protein-protein interaction and binding, and even in micellization and DNA structure is attributed to hydrogen bonding. So, next thing we talk about is that we are talking about what is the entropy of water. Let us think about what happens to the protein molecule. Till now we have not seen what a tertiary structure looks like. We have seen that we have a long polypeptide chain with its R group present in the solvent, present in the water, where it may be forming some hydrogen bondings with it, where maybe those R groups which are aliphatic and non-polar will try to be hiding away from the water. So, once that has happened, it is still not giving us an idea what is the direction in which it will go towards a native state. So, we will see that you have a polypeptide chain which is not having any definite structure. First of all, it is having high entropy. Entropy is a term which we are using whenever we are talking about number of conformations possible, number of freedoms that are possible for any molecule. So, a long chain is having all the freedom to have any conformation, but when we talk about structure and function, we will realize that you have to come down to a minimum number of conformations for any protein to be active. So, we have to think about two things. Now, we have a long chain molecule present in water. This long chain molecule is having several degrees of freedom. Remember, you had the polypeptide and you had the rigid and planar peptide bond, which did allow you degrees of freedom along the chi and phi angles. So, there are around 3 degrees of freedom because of the Ramachandran angles that can be attributed to a polypeptide chain. Once these degree of freedom is attributed, that means every time if we say entropy should be high, that means always the protein should be unfolded, but you know that it is not always the case, and we have to go towards a protein which is having less number of entropy. So, what are we saying? We want to increase the entropy of the water, but we want to decrease the entropy of the protein. So, with this idea, we will further talk about what is the basis of protein structure when we talk about restricting the entropy of the protein and enhancing the entropy of the solvent. So, we stop here now, students. Welcome dear students. In this session we will summarize what is the role of entropy and enthalpy in the protein folding and in the protein stability. Also, we will first revise what we have studied about what are the components that give rise to stability of tertiary structure. We had summarized all the interactions, that all the non-covalent and one covalent, which was the disulfide bridge. These interactions were responsible for the tertiary structure, and we were trying to go from a polypeptide which was free in the solvent water system and how it was undergoing conformational change to give rise to some tertiary structure, which eventually we will call as the native structure. So, our aim was to reduce the degree of freedom and get in the end a well defined state. So, we have to take care of the rigidity of the peptide bond, and we had studied how there are only 3 degrees of freedom per peptide bond, and we also saw that you could not have all possible conformations because there are going to be distorting bonds, there are going to be bonds which will have lot of steric hindrance, and you cannot overlap the orbitals of atom beyond a certain limit, and that is called the van der Waals radii. So, without this constraint, if we had to think about how a protein folds, then the peptide is going to be free to adopt as many as structures and structurals and conformation it can have, and eventually we may not ever reach an end to having just one type of conformation. So, our aim is to go from all these n number of degrees of freedom towards one global stable state. So, summarizing that, we were talking about how hydrophobic effect is a very essential component in structuring of water, which results in turn into conformational stability and structuring of the polypeptide. So, the water tends to form ordered cages around the non-polar groups, and that resulted in the decrease in entropy of the system, which was not favorable. And whenever such non-polar interactions with water are reduced, and that happens with the hydrophobic collapse around of the polypeptide around such non-polar groups, then you have slight increase in the water entropy. These hydrophobic collapse of the protein is always accompanied and guided by the hydrogen bond formation between favorable functional groups. So, any situation that minimizes the area of contact between water and a non-polar R group is favorable, and it increases the entropy, and this we talked about resulted in clustering of the non-polar groups which came together. These non-polar groups, when they came together, further resulted in the van der Waals interactions, which gave very weak but cumulatively large stability to the protein structure. So, we are talking about two things here, and the stability of the protein hangs in the balance. What do we need it to be so that it is stable? First thing we should understand is that we are talking about the free energy, which is delta G, or first I will say G, which is the free energy, and delta G is the free energy change of a molecule when it is folded and of a molecule when it is unfolded. So, when you are looking at the free energy of a folded and an unfolded molecule and the difference between the two, we are talking about delta G, change in free energy. It is governed by the enthalpic, all the electrostatic bonds that you were talking about, and then it is also governed by the entropic. But temperature, we can say we are talking about room temperature. So, eventually we need to have the free energy change for any spontaneous process. We would prefer it to be negative, that's a thumb rule, we cannot change that. So, for any spontaneous process, delta G has to be negative. To get towards that, we have all the interactions that are occurring here which are positive. So, if I say a molecule, if a long polypeptide chain is having only and only those amino acids which are electrostatically which have ionic groups and that can form electrostatic bonds, then what will happen? This delta H is going to be extremely high. Another thing, all those R groups which are capable of ionic bonding will also show ionic bonding with the water molecule, hydrogen bonding with the water molecule, and again it will result in slight decrease in the entropy of water. However, this increase of delta H will not be very favorable. So, that is what we say, that a protein is going to be a balance between the aromatic, non-polar as well as polar charged groups, and that will result in the final stability of the protein. So, we have to have a more negative enthalpic change and a more positive entropic change. So, when we just see this when we see this sentence, it comes to our mind that we want the entire system to have more and more entropy, and if it is going to be like that, then how are we ever going to reach that point or that conformation which is more stable? So, all the enthalpic contributions of the electrostatics and disulfides are not at all the driving force that will govern protein to fold, that we have understood from here. So, the stabilizing and contributions to the Gibbs free energy are going to come from the delta S, and what we are trying to achieve here is, so keep constantly thinking about all the interactions. We are trying to achieve that there should be negative delta H and a more positive delta S. Eventually what you will have, either you have a minus delta H minus T delta S, that will result in a more negative term, or you have such high delta S that if you subtract T delta S out of delta H, you will always result in a negative entity. So, what is the balance, and how can you, within the knowledge that we have got till now, what are the contributors to these two aspects, we have to work out how protein is going to fold. So, protein conformation is stabilized by weak bonds. Delta H cannot be extremely high, we have understood from this equation. So, bondings, you will have hydrogen bonding, solvation, disulfide bondings, and all the hydrophobic areas are going to be buried in the protein interior, so that they contribute to the entropy of the system. We will try to maximize the number of hydrogen bonds. Either you maximize the number of water with the protein hydrogen bond, or there are going to be maximize the number of inter water hydrogen bonds. So, the margin of stability, the delta G is very low. You will have around minus 10 to minus 50 is the difference between a stable folded conformation, and this margin we have to see, if we can reach that margin, we are safe, we are having a native protein, otherwise we are having a denatured protein. Another aspect of this very small margin is that when we are talking about proteins, they are not very rigid molecules. These molecules show very dynamic properties. You know that proteins take part in metabolic processes, binding processes. So, for all enzymatic activity, for binding, there has to be some structural conformational flexibility, so that it can undergo a change or it can allow a change and hence pass it on to the substrate also. So, not every mechanism is lock and key kind of enzymatic process. When we understand more about protein catalysis, you will realize flexibility is also very important. So, this margin, a very small margin of being folded or unfolded, hence becomes essential, and we will explore how we can use this for carrying out all types of bindings and all type of catalysis. So, protein stability is the net balance of forces which determine whether a protein will be in its native conformation or will it be in denatured state, and we are talking here about the thermodynamic stability of the protein. So, first we should understand with this equation what is the Gibbs free energy and what are we talking about and which direction we want it to go. So, H is the enthalpy, which is heat of formation or breaking of bonds. So, enthalpy is going to be exothermic or it will release energy, then delta H is less than 0. Delta H is going to be greater than 0 and it is going to be endothermic, that is this will require to have energy taken up by it. So, many times bond formation will take up energy and bond breakage will release energy. Delta H is, we are talking about in terms of all the non-covalent and covalent bonds, the covalent bonds except all the backbone peptides. We are not talking about that stability as in the previous slide, we are talking about the thermodynamic stability. We will see how even the peptide bond backbone can be broken and we can have a chemical breakdown of the molecule as well. But right now we are talking about all those non-covalent and the disulfide bonds which are contributed to the enthalpy. So, for any stable protein, delta H must be large negative, and what we want here, delta H is going to be exothermic. We would prefer it to be an exothermic enthalpy. Then entropy, which will tell about how many conformations or freedoms that are possible for the system to dissipate its energy. This entropy should always be positive. It will be positive if the delta S is greater than 0, the system is going toward disorderedness, which is a favorable thing. We are talking about the system here in the entirety, protein plus the water. Then this delta S, if it is less than 0, the system is moving towards orderedness or the cage like condition, which is not favorable. And this is a state function, so it will only depend on the final and the initial state. So, S final minus S initial, and we will get the change in entropy. You cannot find the path that a system takes towards decreasing or increasing the entropy. You can only calculate it by looking at the entropy at the start and the end of the process. So, entropy first thing of the water, and secondly we will have to correlate it to how entropy of the protein ensemble is going to be reduced. The number of conformations of the protein has to be reduced. What is the word ensemble here and how do I correlate it to the term native structure of the protein? So, this is the ensemble which is, we are saying, equivalent to a native state. At the very beginning of understanding protein folding, we should understand that a native state is not just one unique state of protein polypeptide. It is not just one type of conformation that if you have 56 hydrogen bonds with water and 10 electrostatic bonds, then only you will have a native state. There is going to be change, being hydrogen bonds being transitory, there is going to be a moderation or a modulation of the structure, and in any ensemble what you have is that you have a free polypeptide, it can undergo flexible conformational changes around the global minimum, and that will result into some set of structures which are nearly thermodynamically same. So, even when we look at a structure here, these are overlapping chains of the same polypeptide and all of them contribute to the native state. So, the native state of a globular protein is defined as the small ensemble of compact conformation reached under folding conditions either in vitro or in vivo, and in the native state all the protein is going to be stable and it is going to be functional. But still again, native state is not just one unique state, it is a ensemble of these compact conformation. All of them are going to have a secondary interactions, will have tertiary interactions, but there is going to be some variation between all of them. This state will be characterized with compactness, low entropy of the polypeptide and low intramolecular enthalpy. And the solvent molecules surrounding the folded protein will also take advantage of entropy of the water. Since large amount of these water molecules are not going to be involved in interaction with the hydrophobic protein interior. So, this native ensemble will have the protein core with hydrophobic groups. So, when we are talking about this, the second law of thermodynamics will state that entropy of the universe is forever increasing and there is no turning back. If we are trying to reduce the entropy, if we are trying to increase the conformational entropy, if we are trying to reduce the conformational entropy of the protein, then in the universe we will have to compensate and have some place where entropy is eventually going to increase, and that let us not be the universe very far away, it is going to be just the surrounding water. We are looking at protein, if only we are to talk about a protein polypeptide present in vacuum, then yes, it is fine, we are going towards a place where there is least entropy, we are going to a more structural compact state. But we are always talking about a protein in a solvent, we have water associated with it. When protein folding occurs, it is either occurring in vitro where also you have buffers, ions and water present, and whenever it is occurring in the cell, you have cytosol, all the molecules, chaperones and ions and water always present around it. So, protein will always be associated with water, and whenever this entropy component we are going to talk about, we are going to take the entropy, reduce the entropy of the protein and give it back to the water. So, we have the enthalpic contributions, let us summarize them and also look at what is their bond strength and energies associated with them. So, you have ionic salt bridges which is having electrostatic forces which are attractive, very strong forces, all the R groups of your acidic and basic amino acids, these are having very high strength, 1 to 6 kilocalorie per mole. You have hydrophobic which is also 2 to 3 kilocalorie per mole, and these are also attractive forces, but you also know that hydrophobic effect has to balance the hydrogen bonding. So, you have hydrogen bonding which is a weak interaction, 2 to 10 kilocalorie per mole. Van der Waals are weakest of electrostatic interactions, less than 1 kilocalorie per mole. Aromatic or you can say hydrophobic interactions, R group interactions are 1 to 2 kilocalorie per mole, and aromatic with amino groups which tend to form hydrogen bondings are around 2.7 to 4.9 kilocalorie per mole. So, it is giving you an indication that if you have these interactions present, they are contributing to the delta H component, which unfortunately we would like to reduce as much as possible. So, when we are talking about protein stability, we have studied the equation of delta G is equal to enthalpy minus T delta S. There is another way in which we can talk about protein stability. But for that, let us look at this component. We have a protein which is your native protein, which is the ensemble of all the native like compact low entropy conformations, and you have a denatured protein which is not at all compact, it is highly entropous. So, first let us determine that there is going to be present at any equilibrium normal protein or native protein and will be denatured protein always present in a system. When we talk about chemical equilibrium or any equilibrium state, we are talking about the reaction is going towards one direction or going towards the other direction. Is the reaction favoring the folding or if the reaction is favoring the unfolding? So, when we are talking about what is favoring the reaction, there are few terms that are going to come, and simple A gives rise to B type of reaction. If you think, you can always find what is the ratio of A and B, and that is what we are doing here. So, if we can find the equilibrium constant of this reaction where we are going from an unfolded to a folded state, we can give the equilibrium constant of such a reaction by which is going to be equal to number of native molecules divided by number of unfolded molecules. And this will also tell us about a very important thing, that you can use this K equilibrium to find the delta G. We know we cannot find delta G directly, we can only find delta G, we can only find the free energy of the system, but we of the native and the unfolded, but we can only see the change in the free energy of the system. And with this very easy equation, we can directly find what is the free energy change. So, we can, if we can find what is the ratio of native is to unfolded, we can talk about the K equilibrium. There are few things we can understand with the K equilibrium. What are the values of K equilibrium which will favor a folded state and which will favor an unfolded state? So, you have K equilibrium which is greater than 1, which will favor the folded state. If it is going to be lesser than 1, it is going to favor the unfolded state. And if you have K equilibrium equal to 1, that means in the solution both the unfolded and the native state are present in equal numbers. When we have these square brackets, we are taking it as the concentration of or number of molecules which are native versus number of molecules which are unfolded. So, we can say very simply say that what is the ratio of unfolded to native. If we want to find that out, we can simply take the K equilibrium value. Here K is equal to minus G by RT, and solving this we get 2 into 10 raised to power 7. That means if there are n number of molecules such as 2 into 10 raised to power 7, then for every native there is one unfolded molecule. But this unfolded molecule is never going to be 0, because we are talking about an equilibrium constant, we are talking about a ratio. This U is never going to be 0. Always the protein folding will be favoring either the folding state or will be favoring the unfolded state, but there would never be a time when you will have entirely all the molecules folded and entirely all the molecules unfolded. And also this will also talk about when we were talking about ensemble. An ensemble is not going to be absolute also because of this relationship, that you will never ever have 0 unfolded, you cannot have 100% folding. So, once we understand this, we are also understanding about what is an ensemble. Ensemble is several protein molecules. Whenever we take in solution, we take not just one protein molecule, we are taking either a mole of a protein molecules and then giving it the right optimum conditions for it to fold. We can shift the equilibrium towards more folded conformation, we can shift the equilibrium towards unfolded conformation, but we cannot have a state in which all of them are native. So, we are talking about transient nature of folded state. This again will tell you that the free energy is so low that you cannot have large difference between the folded and the unfolded state. Second thing we can say is not always, you can never have entirely folded or unfolded state. Secondly, thirdly, if we see that if you allow any protein to refold spontaneously and the rate constant is rate constant Kf of folding is 1, then rate of spontaneous unfolding is also 10 to the power minus 7 per second. So, this gives a half life of 80 days. That means if you are going in the forward direction where you are going towards folded state, backward direction is also actively working, taking it towards the unfolded state. Then we will talk about what is the impact of delta G. We could calculate delta G from the K equilibrium formula. If we take that K equilibrium, so we can get delta G, which is the free energy of native minus free energy of unfolded, and K equilibrium was the ratio of native is to unfolded. So, putting in this equation minus R, which is the constant, T in kelvins, we take a natural log of K equilibrium, we simply can calculate delta G. So, when we can calculate delta G, we can understand what is the what is the conformation which is getting favored. Also, it will tell us what is the value of delta G coming out to be and what are the implication of those values. So, we say that decreasing the energy of the folded state or increasing the energy of unfolded state, we are not going to cause any change in the delta G because it is just the difference between the two. So, this is going to be delta G without any implication, either you subtract u minus n or n minus u, you are only looking at the change. This delta G, if it is going to be lesser than 0 or it is going to be negative, it is going to favor the folded state. If it is going to be positive, it is going to favor the unfolded state, and when you have delta G, it is going to favor an equal concentration of unfolded and native state. So, we understood that there are going to be, how can you calculate the ratio of folded and unfolded conformation? We will see in subsequent lectures. We can talk about them theoretically, but is there any experimental method? What are those methods by which we can calculate the n by u ratio? And if we can calculate the n by u ratio, we can talk about which direction is the folding proceeding. So, in this lecture, we could summarize what are the contributors to enthalpy, all the electrostatic interactions. We talked about the contributors to entropy, entropy of the system as entirety, the system constituting of the protein as well as the water. We also took into account what is the second law of thermodynamics still working at protein folding level, where you minimize the conformational entropy of the protein, but you enhance the entropy of the water with this transient hydrogen bonding, and still our second law of thermodynamics is favorable, and it is true in this case also. So, we have been able to understand little bit about the terms that we encounter, and we will study more about how thermodynamics of protein folding is going to work for us in looking at globular proteins. Thank you, students.
Okay, on that note, I would like to thank ma'am for this very enriching discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.